Good afternoon, everyone. Welcome to another seminar of the cycle of seminars of the astronomy department here at the IAG. Today, we are very pleased to have Professor Rubens Machado with us. Many thanks, Rubens, for being here with us, sharing your work. So let me just briefly introduce Rubens for those who doesn't know him. Rubens Machado got his bachelor degree in physics from the Physics Institute of the University of Sao Paulo and made his master and PhD studies here at the IAG, where he also had a postdoc position. He was also a postdoc researcher at the Andrés Bello University in Chile. And currently, Dr. Machado is a professor at the Universidade Tecnológica Federal do Paraná. His research is based on numerical simulations in galaxies and clusters of galaxies. Today, he's presenting ramp pressure stripping in galaxies that cross a cold front. So please, everyone, turn off your cameras, your microphones during the presentation. The questions will be asked after. If you are in the Google Meet, you can raise your hand. If you are in the YouTube, you can write your question down. And if you want to ask in Portuguese, please go ahead. Rubens speaks Portuguese, so there's no problem. Rubens, whenever you are ready, you can start your presentation.
Thank you, Maria Vitória. Good afternoon, everyone. Let me start by thanking the organizers for the invitation. It's a pleasure to be giving a seminar here at IAG, even if remotely. And I'm going to talk about some recent results of our work on this topic of ramp pressure stripping in galaxies that cross a cold front. Now, the motivation for this work is the following. We know that ramp pressure strips gas from the interstellar medium of galaxies as they move through the gas of the intracluster medium, and this may lead to the development of jellyfish tails. Now, we also know that the intracluster medium gas of galaxy clusters can be disturbed by collisions, and in particular, one kind of disturbance that results in a enhancement of gas density are sloshing cold fronts. And then our research question here is what happens when a galaxy crosses these contact discontinuities. So in a sense, we're joining together these two mechanisms. So I would like to start by giving a very brief overview of both of them. First, ramp pressure stripping in jellyfish galaxies, and then sloshing spirals, before moving on to the description of the methods that we have been implementing and some preliminary results. So first, ramp pressure stripping and how it causes jellyfish galaxies. Starting out with a very brief review of the properties of the intracluster medium, we're talking here about galaxy clusters. Now, galaxy clusters are associations of galaxies with hundreds, maybe thousands of galaxies, with masses of 10 to the 14, 10 to the 15 solar masses, and typical sizes of about 1 megaparsecs. The components of galaxy clusters in mass are very roughly speaking about 80% the dark matter halo, 15% the intracluster medium gas, and about 5% galaxies. We're interested here in the properties of the intracluster medium gas, which is a very low density gas, a hot ionized gas that emits X-rays because of the Bremsstrahlung mechanism. Now, as the galaxy moves through the gas of the intracluster medium, it gets part of its gas removed due to this mechanism of ramp pressure. This is just a brief illustration of a generic simulation showing here the density of the gas. The ramp pressure mechanism regards gas acting upon gas. So this is to say that this is a wind that acts on the gas of the interstellar medium. In other words, the wind due to ramp pressure does not blow stars away from the galaxy, but only the gas. The run pressure depends both on the density of the intercluster medium and on the relative velocity between the galaxy and this gas. In observations, as well as in simulations, we actually see this mechanism working. So we see here not only gas being removed from the galaxy, but we see stars in the tail. This doesn't mean that the stars were removed from the disk of the galaxy, but rather that they were formed in situ, so to speak. What happens is that when the gas is blown away from the galaxy, small clumps of dense gas may still form stars before the gas gets mixed with the rest of the intracluster medium. So I'm showing here just some examples of observations of jellyfish galaxies. By the way, you'll notice that I'm using the term jellyfish galaxies rather generously, in the sense that any galaxy that exhibits features of ram pressure stripping ends up being referred to as a jellyfish galaxy, even though perhaps the term should be reserved only for galaxies that present a more exuberant jellyfish tail. But in any case, I'm not the only one to stretch this nomenclature. So anyway, we have here two galaxies showing signs of ram pressure stripping. And in the next two slides, so this is an image in the optical. This is data from GASP, which is an important current project making detailed observations of galaxies undergoing this process. GASP stands for gas stripping phenomena in galaxies with MUSE, whose PI is Bianca Poggianti. By the way, I took this slide borrowed from a presentation by Yara Hafe. So in this first slide, we see observations in the optical for a sample of galaxies, and in the next slide are the same galaxies, but observed in age alpha. So this is very instructive. A broader view of these kinds of images can be found in the link below. I'm going to flip back and forth a couple of times to compare the optical with the age alpha. And again. So you can see that there are many cases where the tails are very prominent when looking at the gas. To look in more detail at some of these examples, I highlighted a couple of galaxies here. Again, comparing the optical with age alpha. So, for example, in this situation, it seems reasonable to assume that the galaxy must be moving along this direction and leaving behind this tail in the direction opposite to the motion of the galaxy. This is another example where presumably the galaxy is moving face on towards the gas. This may be an example of an intermediate inclination, with the galaxy receiving the wind at some intermediate arbitrary angle. And this might be an example of a galaxy moving edge on, receiving the wind edge on. Now, this is interesting because this is the sort of morphology that appears spontaneously in simulations. So in the next slide, I'm showing not observations, but rather the results already of some embodied hydrodynamical simulations, just to illustrate the fact that, I mean, the simulation was not particularly tailored to reproduce any specific observed galaxy. And yet it's more or less resembles the kind of morphology that we see in this type of observed galaxy. Here also showing the simulated gas and the simulated stars. So in this example, this is a galaxy which is moving. So this is the direction of motion of the galaxy. So it's moving in this direction, receiving the wind edge on. And this is another simulation where the galaxy is receiving the wind face on. So just to illustrate that using these hydrodynamical simulations, we can, in principle, study the morphology of the gas in these jellyfish galaxies. Now, moving to the simulations of jellyfish galaxies, I couldn't review in detail all of the numerous simulation works that have explored this issue. So I'm going instead just to mention, generally speaking, the three approaches that are used to simulate run pressure stripping in isolated galaxies. So the first one is to place the galaxy inside a wind tunnel. I'm going to talk in more detail about this in a moment. Another approach is to simulate not only the galaxy itself, but also the cluster through which the galaxy is moving. And the third approach is to use actually cosmological simulations of galaxy formation and look for galaxies with jellyfish morphologies within those cosmological simulations. So very briefly here, the first idea, not to use a wind tunnel, the idea here is to place the galaxy at rest at the center of a box of, in principle, uniform gas moving at a given velocity with a given gas density with periodic boundary conditions, meaning that the gas that leaves one face of the box re-enters on the other side. And this is a very computationally convenient setup because then you're limited to simulating only the gas in the immediate vicinity of the galaxy, which is the gas which is actually going to interact with the interstellar medium. So this is one possible approach, and this is a technique that has been often used in simulation works in this area. Another approach is to simulate the gas of the galaxy cluster self-consistently. So we can create initial conditions to represent the dark matter halo and the intercluster medium gas of a galaxy cluster itself. Now, this has the advantage of reproducing the gas density profile of the cluster, so the galaxy encounters gas with more realistic densities. On the other hand, this approach is, so to speak, computationally wasteful because we're wasting, in a sense, numerical resolution in a hugely larger volume than actually necessary because the galaxy is only going to interact with gas along a very small volume of the entire galaxy cluster. But this can be done. For example, this is an image from a former master's student of mine, Rafael Ruggiero, who was a former PhD student of Gaston, also used this approach in his PhD. It works, but as I said, it's more computationally expensive. So what we're seeing here is the gas of the galaxy cluster, and this tiny object here, I hope you can see, is the galaxy itself. So the dynamical range is very demanding in this kind of simulation. And the third approach to study jellyfish galaxies using simulations is to look for them in the output of cosmological simulations of galaxy formation. In this example here, galaxies taken from the illustrious TNG simulation, where we can, where the authors of these works can study the evolution of the jellyfish morphologies, the masses, etc. So anyway, just to mention that these are the typical approaches. I can't review all of the details, but just to mention very quickly the kinds of quantities, phenomena that can be analyzed with these kinds of simulations. So there are many papers that studied the gas loss in jellyfish galaxies, the evolution of the star formation rate, the dependent, which can be either enhanced or quenched, depending on the situation, the effects of inclination, star formation in the tail that I had mentioned, morphological changes in general of these galaxies, and the dependencies on the specific trajectory of the galaxy across the galaxy cluster, and the dependence of the environment, and so forth. So there are many simulation works in this area. Just to mention one of them very quickly before moving on to the next topic of sloshing. This is something that connects already with our question of what happens when galaxies undergo this mechanism in merging clusters, in clusters that are undergoing collisions. So in this paper a couple of years ago, we studied a collision between four subclusters in this cluster here, Abel 9012, in which we found that jellyfish galaxies appear to be found preferentially near the boundaries of ram pressure discontinuities. So this is already an indication that the perturbed intracluster medium gas might be playing some role in the formation of jellyfish tails. So the next topic that I would like to briefly introduce is the idea of sloshing spirals in merging galaxy clusters. So this term sloshing refers to a fluid which is undergoing motion within a container which is also accelerated. So in this analogy, the container is the gravitational field, the total gravitational potential of the galaxy cluster, and the fluid is the gas of the intercluster medium. In particular, the cold gas in the cool core of a cluster. So these are the sloshing spirals. Here's one example. These sloshing spirals, they're seen as an excess in X-ray emission. So they are an overdensity. They have these spiral shapes that extend to a few hundreds of kiloparsecs. This is commonly observed in many galaxy clusters undergoing collisions. This is from a paper by Tatiana Lagana a few years ago, with observed sloshing spirals in galaxy clusters. This also appears very commonly in embodied hydrodynamical simulations, as I'm going to show in a moment. And the conditions necessary for the formation of these sloshing spirals are, first, we need to have a cool core on the main cluster. This is the cold, dense gas that is going to be removed from the core. And we need a non-frontal collision. In other words, we have to have a collision in which the perturber encounters the main cluster with an impact parameter. So this is this video here serves as a generic illustration of the mechanism. What we're seeing here is temperature. So that the temperature of the intercluster medium. Blue is cold, red is hot. The secondary cluster, the perturber, passes some hundreds of kiloparsecs next to the main cluster, and we see here the development of the sloshing spiral, which, as we can see, is a spiral of cold gas. So the gas in these blue regions is colder and denser than the gas in its surroundings. I should also emphasize that, I mean, this is a common misconception. The sloshing spiral, first, it extends hundreds of kiloparsecs. It has nothing to do with the spiral arms of galaxies, of course. But second, the shape of the spiral is not at all the trajectory of the perturber. Not at all. The perturber is already many hundreds of kiloparsecs away. The shape of the spiral has nothing to do with the orbit of the perturber. Rather, it is cold gas that is being, initially at least, extracted from the core of the main cluster, the cool core of the main cluster. Right. So in this area, we can use the simulations to try to reproduce and observe the features in galaxy clusters. This is one example of a sloshing spiral that we simulated a couple of years ago, about 2025. quickly here, this is another example that a former student of mine, Nadia Dobrev, simulated during her master's degree. Also a cluster with a sloshing spiral, in this case caused by a recently discovered structure. Last year, we also studied this phenomenon of sloshing spirals in the case of a galaxy cluster that appears to have undergone this process, but with a high inclination angle. In other words, this is possibly a cluster with a sloshing spiral seen nearly edge-on. Okay, so these are just some examples of what we can do with simulations of sloshing spirals. So what matters for our approach here today is that this sloshing spiral is a cold front. It is a region with higher gas density and lower gas temperature than its surroundings. And then the question is, what happens to the process of rim pressure stripping when a galaxy, for example, crosses this region? So if a spiral galaxy had approximately this trajectory, then entering and then exiting this region of overdense gas, what would be the implications for rim pressure stripping? So this is our setup. So the aim of this work that we have been doing lately is to construct an idealized wind tunnel that approximately mimics this structure, the structure of density and temperature that resembles a sloshing spiral. In other words, we need part of the gas in this box representing the hot, low density, unperturbed intercluster medium. And then there is a discontinuity that leads into a region of dense, cold gas, and then another discontinuity, which then brings the galaxy back to the unperturbed gas outside of the sloshing spiral. So this blue region here would represent the sloshing spiral. And the question is, what happens if a galaxy goes across this region? So this is a work that we have been doing lately with, Vismelo Terencio, which is a master student here in Curitiba, and Gastão, IAG. Right, so let me explain briefly what is the numerical approach that we have been doing to construct the initial conditions. There are several stages of preparation, and then I'm going to show some of the recent results. So first, we create initial conditions for a disk galaxy. This is a common. There are tools to create initial conditions for normal disk galaxies. The galaxy is composed of a dark matter halo. There's a stellar disk with a certain fraction of stars in the bulge, and a certain fraction of gas particles in the beginning of the simulation. The simulations that we have been running, we're using the code Arepo, which is a sort of a descendant from the gadget. So the n-body part is similar to the earlier gadget codes. The difference is in the hydrodynamics, where instead of using the approach of SPH, which is a smooth particle hydrodynamics, it uses a more complicated method of a moving mesh. And in this version of the code, cooling and star formation are included. So to proceed with the simulations, we took the following steps in order to prepare the galaxy for the actual simulation. So what I called here these phases 1, 2, and 3 that I'm going to describe in a moment are the following. First, we create an isolated disk galaxy with the components that I just mentioned. And this galaxy is allowed to relax in isolation for a certain period of 1 gigayear in this case. And the idea is just to ensure that any numerical transients will have had time to subside. And then we start with a galaxy that is hopefully more realistic, free from spurious numerical effects. And then there is a second phase also of relaxation, in a sense, during which the galaxy moves already inside a wind tunnel, but this is a uniform gas. This is a wind tunnel containing gas of uniform density and constant velocity. The idea here is that if we started the actual simulation to produce the results to be actually analyzed already with the discontinuous setup that I'm going to describe in a moment, then we might also be causing some numerical transients that should be avoided. In other words, if we take a galaxy that was created in a vacuum with vacuum boundary conditions, an isolated galaxy, and this initial condition is placed instantaneously within a box of gas, then in the first moments of this simulation, the galaxy will not be in equilibrium because it will have been instantaneously transplanted to a gaseous medium that surrounds it that wasn't there in the creation of the initial conditions. Anyway, so the point of this phase 2 of relaxation is to allow the galaxy to already start going through the run pressure stripping mechanism before the actual simulation. So in the early phase, in the early time steps of this phase 2, the galaxy will encounter instabilities which are unphysical, which are merely numerical, because it is not yet in equilibrium. But the later stages of this phase 2 of relaxation might actually be interpreted as being physical, in the sense that they could represent the prior trajectory of the galaxy across the intercluster medium before the galaxy enters the cold front. So after the first few moments of accommodation, then the galaxy travels for about 0.2 gigayears through a constant density gas, which may not be identical to the density that a galaxy might encounter in the real world, but during which the run pressure stripping might be a reasonable approximation. And then there is the third phase, which is the actual simulation, where the actual mechanism that we wish to analyze is going to take place. So let me show the results of each of these three phases in sequence. First, during the phase of the isolated galaxy being relaxed in vacuum boundary conditions. Like I said, this is just for a mechanical gravitational accommodation of the galaxy. There is still no run pressure acting, but in any case, the end of this phase 1 of relaxation leads to these frames here, which are a normal morphology of a disk galaxy. We're seeing here the gas and the stars. So this is a reasonably reliable initial condition to move forward to the next phases. And then phase 2 of relaxation consists in placing that galaxy extracted from t equals 1 gigayear of the previous phase inside a box, a wind tunnel. So this is a box with these dimensions here, 75 by 75 by 150 kiloparsecs. This box holds gas of constant density, and the gas has a constant velocity along the direction, the longest direction of this rectangular box. In other words, if the galaxy is placed here at rest in the origin, the galaxy will encounter the wind face on. And this box already has periodic boundary conditions. So this is the end. So this is phase 2. At the end of phase 2, this is what the galaxy looks like. So we have two cases. There is one case, LD here stands for low density and HD stands for high density. So there is one box with this density here, 10 to the minus 28 grams per centimeter cubed, and another case with high density. So in the end of this phase, we should compare this frame with this frame. So the galaxy is moving face on. We also see this view of the galaxy, but we could focus here on the edge-on views because this is where the tail is visible. So already the difference between these two galaxies is that the one that moved for 0.2 gigayears through the high-density gas naturally developed a more pronounced tail of gas, and we can already see that the size of the gas disk in this case is already smaller than the size of the gas disk here. Now, these two snapshots, this one here in the low density environment gas, and this one here in the high density environment, they are placed in the beginning of the third phase, which is the actual simulation. So in the actual simulation, we have a gas box, a wind tunnel, which is not constant density. So the idea here is that so we could focus maybe on the right column here. So we're seeing here temperature, density, and pressure as a function of the major axis of the rectangular box. So the idea is that we start with the ambient gas with a certain density, and then we have three cases. In these three cases, we have the sloshing spiral being an overdensity by a factor of 2, which is the green, by a factor of 5, and by a factor of 10, which is the orange and the blue here. Now, if the gas density is increased in the sloshing spiral by factors of 2, 5, and 10, then the temperature of this gas needs to be decreased by the same factors, 10, 5, and 2, in order to keep the product of density and temperature, in other words, the pressure, constant, because this is the defining feature of a contact discontinuity, which is what sloshing cold fronts are. So in a contact discontinuity, the temperature and density are discontinuous at the entrance and the exit of the sloshing spiral, but the pressure is continuous throughout. In this figure here, we can see the galaxy and the gas in the intercluster medium. The blue particles represent the gas, and the wind velocity is falling towards the galaxy in this direction, and the galaxy develops a jellyfish tail, which are the green particles here, where I'm separating in the visualization the interstellar medium that is retained by the galaxy, and the gas that has already been removed from the galaxy. And the idea, we can see in this image that the galaxy is at this moment at the low density gas, in other words, outside of the cold front. The galaxy remains stationary at the origin, but the blue particles, which represent the gas of the intercluster medium and the sloshing cold spiral, these blue particles, they move towards the left as the simulation progresses. So then the galaxy encounters, I think it's in the next, yes. So the galaxy encounters, given the lengths and the velocities and the times that we implemented, the galaxy will encounter 50 kiloparsecs of ambient gas, followed by 50 kiloparsecs of cold, dense gas, dense gas of the sloshing spiral, and then followed again by an additional 50 kiloparsecs of ambient gas outside of the sloshing spiral. In this video, we have two cases with low density and high density, and each one of these cases has the amplitude of the discontinuity by factors of 2, 5, and 10. I'm not going to show all of the 6 simulations, but as an illustration, here is one case of low density gas with a density contrast of 1 by 5. In other words, this is one of the cases of weak run pressure, so to speak. Yeah? So perhaps we should focus on the left. The galaxy will encounter the denser purple gas. The galaxy goes through the dense gas and then moves for a certain while, more or less outside of the gas. Okay, so the galaxy here, I should play it again. The galaxy develops a little bit more of a jellyfish tail, but not very striking, because this is one of the weak cases, right? And in the next video, this is the strongest case. So this is the case of high density with a contrast by a factor of 10, meaning that in this case, the galaxy will enter a region where the gas is denser by a factor of 10 and also colder by a factor of 10. Now, so this galaxy already starts with a substantial tail, then it enters the cold front. And in this case, the gas is strongly removed. I should play this again. So the galaxy starts already with a considerable tail because it had been moving through phase 2 in a constant density. In a constant density medium. Let me play the video again. There. So the purple here is outside the cold front. The orange colors is the denser gas. And as the galaxy moves through the denser gas, it undergoes a lot of ram pressure stripping. Right. So this is the global result of all of the 6 simulations as a function of time. Here on the left, we have the low density cases. Here on the right, the high density cases. The columns are the factors of 1, 5, and 10 for the low density, 2, 5, and 10 for the high density. And the rows are the time. So the beginning of the simulation on top and the end of the simulation here in the bottom. So perhaps we should compare these 6 frames here in the bottom, and we can see that the galaxy moving through the high density simulations, they develop a much more noticeable jellyfish tail. And also there is perhaps some noticeable dependence, not only with the absolute density itself, but with the contrast in density, these factors here, 2, 5, and 10. Right, so this is the idea of the simulations. I will just show very quickly now some preliminary results. I should emphasize that these results are preliminary in the sense that they might still change as we improve certain numerical details of the simulation approach that we adopted regarding the size of the box and other issues that we're still looking into. In any case, here are the preliminary results. First, the gas loss, or actually, in other words, what we're plotting here is the gas retained in the interstellar medium of the galaxy in the 6 simulations. The beige and brown colors here are meant to depict the density of the gas. So we have here low density in the left, high density on the right, and the amplitude of the discontinuities 2, 5, and 10. The blue lines are the actual simulation through this layered wind tunnel. And the black lines are what would have happened to the galaxy had it continued on a uniform box instead of the layered box that mimics the cold front. So we can clearly see that the high density cases, the galaxy loses more gas than otherwise, and also that when the amplitude of the discontinuity is large, in other words, 1 by 10, the gas loss is also much more pronounced than when it is only a factor of 2. When looking at the star formation rate, on the other hand, we didn't find any very pronounced differences, at least for the simulations that we ran so far. In other words, there was neither a very clear enhancement nor a very clear decrement of star formation rate, nothing beyond maybe 10, 20%. So this is still inconclusive at the moment. Another thing that we measured was the remaining sizes of the gas disks. This might seem like a straightforward detail, but on the other hand, it might be one of the few observables that we can predict so far. In other words, if a galaxy is moving through a sloshing spiral under these conditions, then it is expected that the effective radius of the gas will have been substantially shrunken in the case of high density and high contrast. Anyway, this might be an observational consequence moving further on. The next thing that we analyzed was the properties of the upstream gas. By upstream here, I mean the gas that has not yet been collided. In other words, these are the properties of the gas which is in front of the galaxy, ahead of the galaxy. And what we found here is that apparently there is a compression of the upstream gas due to the arrival of the galaxy. In other words, the motion of the galaxy seems to be causing the gas ahead of it to be somewhat denser than it would have been otherwise in the entrance phase of the cold front, in the sense that the gas density that the galaxy encounters, and consequently the run pressure that is exerted on the galaxy, is increased compared to what would have been just an equilibrium cold front. This is what is shown here as these peaks in the entrance of the galaxy inside the cold front. The secondary peaks I would rather not interpret yet. It might be something physical, but it might be a numerical artifact that we're still trying to clarify. Finally, the properties of the tail. We measured the amount of gas in the tail of the galaxies, as well as the amount of stars. Again, these are stars that were already formed outside of the galaxy in these dense clumps of star-forming gas that have not yet had time to mix with the ICM. And again, we find that it depends both on the density, but maybe more importantly on the density contrast of the discontinuities. Okay, and finally, this is the last quantity that we measured, the effects of velocity. So there is not yet at the moment thorough systematic exploration of velocity, but in any case, just to compare our standard case, which was 750 kilometers per second with a lower velocity and a higher velocity case. And as expected, since run pressure depends on the square of the velocity, the removal of gas is more pronounced with higher velocity, yes, but this is still further exploration to be analyzed in the future. Right, so these are the preliminary results. The perspectives moving forward, we're trying to focus mainly on making computing observables from the simulation. So the idea would be to calculate from the output of the simulation the evolution of the colors of these galaxies, but for this we need stellar ages and stellar metallicities to use in stellar population synthesis codes. We're also trying to make mock images in the optical, in the X-rays, and in age alpha, which should be convenient for comparisons with observations. And from the simulation point of view, we also need to try different parameters such as other inclinations, other velocities, different gas content in the initial conditions. And another curious thing that I would like to explore at some moment is the consequences of run pressure stripping, not only on the gas, but on the morphology of the stellar disk. Apparently, it may lead to warped disks in a rather unexpected morphology. Okay, so given the time, I think I should stop here. I'll leave a link to my homepage, and I'll stop here. Thank you. Good question. So no. So there is no circumgalactic medium present in the galaxy, but this is not a bad idea. No? This is something that could be included without difficulty in the initial conditions, and might have some relevant effects of the interaction between this gas and the gas in the intercluster medium. Although the mass of this gas would be quite small. As I understand it, the circumgalactic medium might contribute with what, 10 to the 9 solar masses, but it's something to be tried.
Right.
Good question.
Maybe the pressure could be important, the pressure of the halo.
Yeah, I mean, it could, I don't know, maybe shield the interstellar medium somehow. I don't know.
Right. I think I have more questions, but later on I ask. I'll leave others.
Betch, you can go ahead.
Oi, Rubens, tudo bem?
Beth, tudo bem?
Okay, fine. Cool simulations. So let me ask you one thing with regard to the presence of magnetic fields. Of course, the strength of the magnetic fields in the intercluster medium is smaller than the pressure gradients, the thermal pressure gradients of this environment. Nevertheless, when you have these, exactly, you are dealing with the run pressure effects in compression regions, right? So you are dealing with the shocked regions. And in these compression regions, you also have the cooling of the gas, right? And so the thermal pressure decreases, and at the same time, the compression increases the magnetic field, which in fact acts as a shielding in the process, diminishing decreasing the strength of the impact, right? And therefore decreasing the strength of the run pressure itself. So you are going to have a balance between the run pressure, the thermal pressure, and the magnetic pressure, essentially, right? So in this sense, because you increase the importance of the magnetic pressure gradients and decrease the importance of the thermal pressure gradients, you may have some kind of compensation between these two, so that the run pressure will act upon them exactly in the same way. So my question is, have you considered or the effects, or have you thought about considering the presence of the embedded magnetic fields in the system in order to take into account this extra pressure that may oppose to the run pressure, and therefore will change the results and the time scale of the evolution of the system itself, and all the behavior, right? And the time scales implied in your results. And if you have considered this or made some predictions, what is your expectation?
I see.
Regard?
I see. Thanks, Beth. This is an interesting issue, but this is not something that we have looked into yet. I know that there are authors that have performed the simulations of this type, including magnetic fields, but I'm not very familiar with the direction of the results that we should expect. But you're right. I mean, in the sense that I mean, the key issue here is the compression of the gas, in a sense. So if this causes relevant
decrease.
effects, yeah. Yeah, so if this changes meaningfully the structure of the magnetic fields, I would guess that it would play a role, but I wouldn't know in which direction to estimate how this might work.
It will decrease. It will decrease the impact over the run pressure, because the magnetic fields, they get part of this, the energy, the mechanical, the kinetic energy, they get part of this energy that would go into internal energy and therefore into pressure and temperature. It goes to the magnetic fields. That's why it will decrease the impact. So in this sense, it would probably make it longer, the process, and the strength of the process would be decreased. The intensity would be decreased by these by the pressure, magnetic pressure gradients, right? Because magnetic fields act really as, you know, a shield. They will absorb part of the impact, right?
I see. Yes, this is something that should perhaps be looked into. Yes, thank you.
You're welcome.
Okay, I have just a comment on that point. You can really make an estimation on how this can affect the act of the ramp pressure upon the galaxy, let's say, simply by making a calculation of the magnetic pressure of the medium and compare it with the ramp pressure. So if they are same order, then it's fine. But I would say it would be very, like, orders of magnitude lower than the ramp pressure. But it's just a guess, just a comment.
Yeah, all you have to do is to calculate the beta, the ratio between the thermal pressure and the magnetic pressure after compression. So considering that the thermal pressure also decreases, and then you are going to get beta and see what is the fraction that goes into of the impact that goes into the magnetic field. That's why I asked you if you had evaluated this in order to make this prediction.
I see. No, this is a good point. Thank you.
Okay, Gaston?
Hi. Thanks, Rubens, for this nice talk. I have a question. It's just occurred to me. You said that the size of the disks, the galaxy disks, would be an important observable to test this. After passing the sloshing or the cold front, they would shrink. So I was thinking, do you think that we could look for that with the surveys like the S+, SDSS, where we can measure systematically a lot of galaxies around sloshings and cold fronts?
Yeah, good question. I mean, I'm not sure how what we would conclude statistically. I mean, in the sense that even if galaxies that undergo this mechanism are systematically decreased in size, the size of the effective radii of the gas. I mean, compared to what exactly? To a sample of unperturbed galaxies of the
other
same
galaxies
morphological type.
Yeah.
Yes, I mean, similar sized galaxies in the same galaxy clusters. Maybe, and like we talked, probably I mean, if this is happening, it can't be for galaxies that have already crossed the sloshing spiral long ago, because apparently if this phenomenon is short-lived, then it would only affect galaxies that are either on top of the sloshing spiral right now, or that have only very recently left the sloshing spiral. So perhaps looking at galaxies under these conditions. And then what I meant by the size being unobservable is that so far we have only simulated galaxies that receive the wind face on. So this is a configuration where we, observationally, we would need to be seeing the sloshing spiral face on, the spiral on the plane of the sky, and we would need to see the galaxy edge on in our observed projection. So then to measure the effective radius of the gas, this is rather inconvenient because then it's the opposite. We would need to be seeing the galaxy more or less face on in a case where the sloshing spiral is difficult to identify. Anyway.
Okay, thanks.
Okay, Marcelo has a question.
Hi, Rubens. Can you hear me?
Yes.
Okay, great talk and nice results. I have two simple questions that I'm curious about. One of them is, what is the average time scale of galaxy cluster sloshing spiral?
Yes, good question. I mean, this is the morphology of the sloshing spiral changes substantially as a function of time. So in those sloshing simulations that I showed, the time scales there are of the order of, let's say, hundreds of mega years. So most of the dynamical change takes place probably within 1 giga-year. But I mean, I don't know if that was the direction of the question, but can we consider the sloshing spiral more or less stationary during the crossing of the galaxy? Then maybe yes, because the thickness of the sloshing spiral would be only maybe 50 kiloparsecs or something. So this is a distance that can be crossed in 0.1, 0.2 giga-years.
Nice, yeah. The other one is, what are the main variables that defines the density contrast of the cold fronts? Is it related with the mass of the clusters, the cluster that is suffering the disturbance, or the cluster that is perturbing this cluster? What are the main variables in scene?
I see. Yes. So I would say that it depends probably on the orbit of the perturber. So if or maybe in a sense the intensity of the perturbation, which would depend both on the mass of the perturber and the distance, the maximum approach. So this should influence the intensity of the sloshing spiral, and then again the timing, the age of the perturbation, because after some 0.5, 1 giga-years, it should dissipate already. So anyway, so we took those ranges, 2, 5, and 10, in order to be roughly representative of more or less realistic contrasts. But yes, I mean, you're right. There is a variety, which will depend on the masses, the orbits, and the times.
Okay, so higher masses and lower density contrasts. That is what I'm thinking.
Yeah, that's the direction that I would estimate as well. I mean, so if the perturber is very massive with a very small pericentric passage, this is the configuration that will cause the most disturbance and probably extract the most gas from the cool core. Yeah, makes sense.
Okay, great. Thank you.
Thank you.
Yes.
Hi, I actually had the same question on magnetic fields, so thank you, Betsy, for asking that. I have a very basic question. If I understood correctly, you are simulating young galaxies, right? I saw 1 giga-year in your first phase of evolution. Is that correct?
Mm-hmm.
Okay. I was wondering if any of your results will depend on longer evolution, like if you had second and third generation stars, if you had, more time to form massive stars, and for example, in change, increase your metallicity in your galaxies. Is this an important parameter?
I see. No, this is a good point to think about. I mean, what the initial conditions mean, because I mean we're not actually simulating galaxy formation in any sense. So our initial conditions, it already represents a circular stellar disk, well established, with a bulge, with a certain gas fraction. In other words, that 1 giga-year of relaxation, that's more numerical than physical, to be honest. And if it is representing something, it's not so much the time since the formation of the galaxy in some sense. It could represent, say, the time it took for the galaxy to fall from the virial radius of the galaxy cluster
to relaxation,
to about 200 kiloparsecs from the cluster center, something like that. But I mean, the point is that the galaxy starts already quite evolved, quite formed in a period of, say, secular evolution of the galaxy.
I see. Thank you.
Thank you.
Rubens, just a doubt about observations. Is it possible to observe in X-rays some features the wake behind the galaxies in the intercluster medium?
Yeah, so this is one of the sources of information. There are several observed jellyfish galaxies,
right,
where we see the tail in X-rays. And hopefully this is one of the observables that we can make mock images without much difficulty in the near future.
Right, because maybe something of interest, also Betty's interest, a PhD candidate here in IAG, is about a parameter in the intracluster medium, which is the viscosity. Maybe different viscosities in the cluster will, the wake will be different, will disappear in a different length or something like this. And something that the plasma community is very interested in this parameter. Maybe you can also test this parameter in your simulations to see if it gives different observables for the wake.
Good question. This is also something that might need to be looked into, the viscosity. Yeah.
Okay, so I have a couple of questions myself. I was wondering if do you consider any type of cooling in your simulation of the gas?
Yes, but this is only, I mean, cooling is present in this public version of Arepo, but it's probably not very relevant for the gas in the intracluster medium, because our time scales are very short in the simulation.
I see.
The actual simulation lasts for only 0.2 giga-years, so...
it's not enough for the gas to cool. Okay. And I have another question. I am curious if you can combine your simulations with the observed morphologies of the galaxies and I don't know, establish some limits on the parameters of in the medium mostly. Is this done? Because I am comparing this to what is done, for example, in stars. Like, okay, if you see some feature of the wind of the star in the interstellar medium, you can make some guesses on the parameters of the interstellar medium or the wind of the star. So.
Yeah, I mean, this is a good question. I mean, I don't know if if based on the the current morphology of the jellyfish tail, if we could make some estimation based on the simulation of the prior trajectory of the galaxy, something like that, to be able to say where the galaxy came from in the prior giga year, say. Perhaps.
I see. Okay, thank you. So, there's more question, comment? No? Okay, let's thank the speaker again. Thank you very much. Rubens, would you like to say something?
That's it. Thank you, everyone. So it's a pleasure to be here. Nice seeing everyone again. Thank you for the organizers.
Okay, thank you.
Thank you, Rubens.
We're waiting for the transmission to stop.
Obrigado. Eu que agradeço. Contente de compartilhar uns resultados preliminares aqui. Vamos ver como que avança nessa